Our first speaker today is Kuznetsov, who will speak about derived Calabi Yau categories and Fano manifolds of the grid chat.
Thank you very much. So it is a great pleasure to speak here in such nice atmosphere, such warm atmosphere, I would say. So I will speak indeed about Calabi Yau categories, in fact subcategories, and Fano manifolds of the grid plane. So, in some sense, the point of view which I would like to show is the following. So, there was an interesting question discussed yesterday in both yesterday talks about holomorphically symplectic varieties which we know. So, you know, if we will speak about compact holomorphically symplectic varieties, then we know quite a few of them. So basically, what we know, so what kind of holomorphically symplectic varieties do we know? So first of all, we can take a K3 surface and its Hilbert scheme, so some Hilbert of K3. So this is one series of examples. Another series is provided by Kummer varieties associated to an abelian surface. And also there are two sporadic examples due to O'Grady. And in fact, all known holomorphically symplectic varieties are deformation equivalent to one of these. And of course, it is an interesting question whether we can construct different examples or whether we can prove that there is nothing else. And of course, if you look at this list, you immediately see that all these varieties are related to either to K3 or to abelian surfaces. So these two O'Grady examples, they are also related to, one of them is related to a K3 surface. So it is a certain desynchronization of some modular space of vector bundles on a K3 surface. And another one is related to an abelian surface in the same way as Kummer variety. So it's these two examples are a kind of high rank generalizations of this example. So in some sense, it is a good question what can be a source of other examples. And to see some possible source, let us look at indeed at other examples of holomorphically symplectic varieties which one can construct, which of course will be deformation equivalent to these ones, but still let me mention some of them. So what are the other examples? So the first and maybe the most famous example is the Fano scheme of lines on a cubic fourfold. So Y in P5 is a cubic fourfold. So it is due to variant analogy. So it is a very famous example. This is a four-dimensional holomorphically symplectic variety, and it is deformation equivalent to Hilbert of a K3 surface. So another example, which is also related to a cubic fourfold, is much more recent. So let me denote it by M of Y. So it is related. So it is a certain 8-dimensional holomorphically symplectic variety related to twisted rational cubic curves. On Y. So it is quite recent, and it is due to Manfred Lehn, Christopher, the second one, yeah?
Christian.
Christian, sorry, Zerger and Van Straten. So this is a more recent example. So it is an eight-dimensional holomorphically symplectic variety. And there are other examples such as double EPW sextic, which I will discuss later in more detail. And another interesting example is a funny example found by Debar and by Olivier Debar and Claire Loisel. So it is a certain subvariety in Grassmannian 610. A certain fourfold. So there are several examples. Each of these examples is known to be deformation equivalent to one of the standard examples in some sense, but still it is good to understand what is the reason. So why these varieties are holomorphically symplectic. And in some sense, a good point of view on these examples is the point of view of derived categories. So in fact, all these examples are very natural from the point of view of derived categories. In fact, if you look at the structure of the derived category of these varieties, of a cubic fourfold, or of the varieties to which these two other examples are related, then you can see a subcategory in this derived category, which is very similar to the derived category of a K3 surface. So, for example, if you take, again, a cubic fourfold, if you take its derived category, it has a semiorthogonal decomposition with three components being very simple. They are generated just by exceptional line bundles. And one more component which carries all the non-trivial information about this cubic fourfold. And this category is of K3 type. Y is of K3 type. Being of K3 type has a completely rigorous mathematical meaning. It is a saturated triangulated category. Moreover, it's Serre functor, which is just a categorical interpretation of Serre duality. So it is isomorphic to the sheet by 2. And if you have an algebraic variety and if the Serre functor of its derived category is isomorphic to the sheet by 2, it means that the canonical class of this variety is trivial. So this isomorphism expresses the triviality of the canonical class in some sense. And also one can check that the Fourfold homology of this category is isomorphic to the Fourfold homology of a K3 surface. It's a graded vector space. It's a graded vector space. And in fact, moreover, you can check that this category is a deformation of the derived category of a K3 surface. So moreover, A1 is a deformation. No. Just this graded vector spaces. I mean, the Fourfold homology of an algebraic variety is just the direct sum of Hodgkin homology with a special gradient. So if you have some x, then its Fourfold homology in degree n is the sum over p minus q equal to m h p q of x, or maybe qp, I don't remember. So in this sense, it has the same gradient. So it has one-dimensional gradient pieces in degree 2 and minus 2, and it has 22-dimensional piece in degree 0. So as a graded space, it is the same. So Yeah, so this category AY is a deformation of derived category of a K3 surface. Namely, one can construct several families of cubic fourfolds for which you can construct such an equivalence, and for generic cubic, this kind of semiorthogonal decomposition can be also done in families of cubic fourfolds, so you can consider the family of these categories in a very natural way. So, clearly, when you deform your cubic fourfold, these categories form a continuous family of triangulated categories in whatever sense you can consider. Okay, so now the point is that as soon as you have a subcategory of this type as a semiorthogonal component of your derived category, it is natural to expect something like holomorphically symplectic variety as a modular space of some objects. Namely, in the same way as when you consider any modular space of sheaves on a K3 surface, it always comes, its smooth part always comes with a canonical symplectic form, which is basically induced by third duality. In the same way, if you have some modular space of objects in this category, then at least at its smooth locus, there will be a canonical symplectic form, which will be a holomorphically symplectic form. And so, if you can consider any modular space of sheaves on your cubic fourfold, for example, such that the corresponding sheaves are objects of this category, the smooth part of this modular space will come with a holomorphically symplectic form. And if you manage to find a smooth modular space, it will be holomorphically symplectic, smooth and cold. So, for example, this is what happens with the Fano scheme of lines.
So it gives you this direction, which you believe, but are you able to work over the expression?
No, unfortunately no. There is no, at least it's, a priori the Cauchy homology is only Z-graded. You categorically, you cannot reconstruct the second grading from the structure of the category.
For the cubic, you do not recover the fact that the H31 is the one.
No, no.
As long as the fact that this one is applicated.
No. H31 is the only term which give you the second or Cauchy homology. So So H31 you reconstruct, but you cannot reconstruct H00 or H44. Yeah, so it's this is okay. And in some sense, this class in H31 is what gives you this isomorphism in some sense. Yeah. So once again, so let me maybe emphasize this. So whenever you have a smooth and compact modular space of sheaves on Y, which live in this subcategory, this modular space is holomorphically symplectic. So, once again, the symplectic form, in fact, is induced by this isomorphism. This isomorphism induces a symplectic form. In some sense, this isomorphism gives you a canonical duality on X1 from E to E for each object, and this is the symplectic form which you want. So, let me show how it goes for the Fano family of lines. So, in fact, it is quite straightforward. If you have a line on this cubic fourfold, then, of course, the first thing you can consider the structure sheaf of your line. the most natural object which you can associate with the line is just its structure sheaf. But of course, this structure sheaf is not an object of this category, just because it is not semi-orthogonal to all these objects. So, for example, there is a morphism from the structure sheaf of Y to E. So you can consider this morphism, and you can take its kernel, which is the ideal of the line. And maybe let me also twist everything by 1, so it will be more convenient to do it in this way. Then if you do it, then this object, you can check that it is semi-orthogonal to these two line bundles already, but it is not semi-orthogonal to all Y. And so to make it semi-orthogonal, you should also take what is called the mutation functor, which means that you take the space of global sections of this sheaf, which is 4-dimensional for each line, and so it gives you a morphism from OY direct sum 4 times to IL of 1. This morphism is always surjective, so you can take the kernel, so let me denote it by FL. So you can call this sheaf the second syzygy sheaf of the line. And so it is easy to check that if you consider the modular space of these sheaves, then this will give you precisely what you want. All these objects will be objects in this subcategory, and the modular space is isomorphic to the Fano scheme of lines, and because all the objects are in this subcategory, it carries a holomorphically symplectic form. So, in some sense, it gives you, I mean, of course, you can do everything here without all this technique. I mean, the result that this variety is holomorphically symplectic is much more simple, but what I want to say is that this gives you a kind of explanation. So the reason why this variety is holomorphically symplectic is just because it can be represented as a modular space of objects of this K3 type category. So if you want to generalize this approach to construct other examples, the natural question to ask is what kind of varieties have K3 type subcategories. Yeah, so, and this is the question which I would like to discuss. And I will give several examples today. So the question is which which varieties have K3 type subcategories as semi-orthogonal components. So can we construct some example besides this cubic threefold? So in fact, it turns out maybe instead of asking this particular question, let me first generalize it in some way. So let me ask not about K3 type subcategories, but about Calabi Yau type subcategories, which means that, so what does it mean for subcategory to be Calabi Yau? I mean, the definition is a straightforward generalization. So A in D of Y is CY subcategory if the subfunctor of this subcategory is isomorphic to a sheaf. And if it is the sheaf by n, then I will call it NCY subcategory. So in some sense, K3 type subcategories is almost the same as two Calabi Yau subcategories. Okay? Some question? Huh? What is what? SO maybe?
No, it's self-functor.
Yeah, okay, it's self-functor. Should I give a definition? Okay. So, let me write it here. So, if you have a triangulated category, so let it be a triangulated category, then the self-functor for T is an auto-equivalence S sub T from T to T, such that for any two objects of your category, there is a functorial isomorphism between cones from F to G dual and cones from G to S T of F. So this is the definition, and an important statement about the Serre functor is the following. So the first statement is that if a Serre functor exists, then it is unique. It is unique. And moreover, if T is a derived category of some smooth projective variety X, then its Serre functor is isomorphic to the tensoring with canonical class and shift by dimension. Okay, and also if you have a semiorthogonal decomposition of a triangulated category, if the category is saturated, then its semiorthogonal component also has a Serre functor, and we can compute it in terms of this semiorthogonal decomposition. So, as you see, for varieties, this Serre functor, I mean, so first of all, it is since it is defined purely in terms of triangulated category, so of course it is compatible with all equivalences of triangulated category. So it is purely categorical information about your category. I mean, it is canonical in the same sense as canonical class is canonical. And also for derived categories of varieties, it has all information about the canonical class and about the dimension of the variety.
This K3 type categories, they will be deformational equivalent to the derived categories of K3.
In this case, or
okay,
in general
in
case?
general.
It is a question.
Okay, if they will, then these modular spaces are going to be deformationally equivalent to the examples of.
They should.
Okay.
At least it is what you expect. Yes. So maybe to prove it rigorously would be not so simple, but still, of course, it is what you expect. I mean, of course, when you deform category, you expect that all modular space is deformed with this category. But I mean, there are some subtle points. For example, when you are speaking about modular space, you implicitly consider some stability condition. And of course, when you deform category, the deformed stability condition may be different from the stability condition which is natural for your another category. So these two modular spaces may be like two modular spaces for the same variety, but with different stability conditions. And such modular spaces are typically only birational. So because objects which are stable for one stability condition may not be stable for another. So, but I mean, in the case of holomorphically symplectic varieties, maybe it is not that bad because you will get a family of birational transformations, and it is known that I think it is known that if two holomorphically symplectic varieties are birational, then they are also deformation equivalent. So at least, I mean, in this way, we will be able to prove that these varieties are in the same deformation family. But I mean, a priori, it is completely not clear. If you find, for example, even if you find a two Calabi Yau subcategory somewhere, it is not clear why it should be. For example, it is not clear why its Cauchy homology will be the same as of K3 surface. Of course,
or abelian surface.
Or abelian surface.
So Fano, as an example, the dimension is always 24 or 16 dimensions.
Is it a question or a remark? I don't know. I don't.
I know examples other than
So the only examples of two Calabi Yau subcategories which I know are either of K3 or abelian type.
But
of course, it doesn't
do
mean
you see any chance how to prove any bound?
I don't know.
But what was your assumption on subcategory? Full?
So assume that it is a semi-orthogonal component
Or semiorthogonal?
which means that it is an admissible subcategory. Or instead you can assume that it is saturated.
The dimension is associated to the option category. How do you calculate the dimension?
Dimensional quantity.
This dimension, this m,
Yeah.
is in the set function.
More or less.
So I'm saying that something is n Calabi Yau if its functor is exactly shaped by n.
But
Why do you consider this other
I mean, so for example, if you have a K3 surface, its derived category has no non-trivial semiorthogonal components. I mean, to have a to be a semiorthogonal component is a very strict condition. No. So the derived category of a K3 surface is indecomposable. And the same is true for any connected Calabi Yau variety. It is a very nice result by Bridgeland. I mean, usually if you have some triangulated category, it is very difficult to check whether it is decomposable or not. But there is a very brilliant observation by Bridgeland which proves that if category is Calabi Yau, and if it is connected, then it is indecomposable. So, yeah, it is a kind of strange thing about derived categories. So, in general, I mean, usually some properties are very hard to prove, but in some cases they are much more simple. And, I mean, it is a kind of unbalanced situation, which is very funny, but I mean, probably shows that we don't understand yet something important.
when you said that the only examples of Calabi, two Calabi categories are K3 or unit type, what do you mean?
Precisely this, that I don't know an example of two Calabi.
Deformation equivalent or such? What is this?
No, I mean that if you have a Calabi Yau subcategory, then its quotient homology as a graded vector space is isomorphic either to K3 or to abelian quotient homology. That's it. A priori, you could have, I mean, a lot of other possibilities, but I just don't know. Okay, so let me continue. So what I want to say is that there is a certain approach which allows you to construct many examples of Calabi Yau subcategories of this type. But of course, most of them will have dimension bigger than 2, but still some of them will be 2 Calabi Yau subcategories. So, and to construct such examples, I will need another definition. So this is a definition, the definition of a Lefschetz semi-orthogonal decomposition. So, of course, I didn't give you the definition of a semi-orthogonal decomposition, but maybe this one will be sufficient. So let me say that. So let X be some smooth and projective variety, and assume that some line bundle is given on X. So M is an X. So I will say that a rectangular Lefschetz decomposition, maybe let me say L Lefschetz, meaning with respect to this line bundle L, decomposition of d of x is just a subcategory d in d of x such that d of x such that if you take d, then b tensor with L and so on, b tensor with L to the m minus 1, So the condition is that this is a semiorthogonal decomposition, which means two things. First of all, it means that there is a semiorthogonality between objects of these subcategories, and also that these subcategories generate the whole category.
L is ample or not necessarily? Just an.
I mean, for this definition, it doesn't matter.
Yeah.
And in many interesting examples, it is not ample, but says semi-ample. But I mean, a priori, you can consider arbitrary L. For example, you can take L to be the trivial bundle. But of course, then the only decomposition will be the trivial one, only one component. So, so let me say more explicitly what does it mean. So first, it means that for any object of this subcategory B, if you compute X spaces from F tensor L to the K to F, it is 0 for all K from 1 to M minus 1. Yeah, that's correct. From F1 to F1. Okay, so this is the semiorthogonality condition, and the second condition is that V of X is the minimum triangulated subcategory. So maybe let me see. The minimum triangulated subcategory of V of X containing B tensor L to the K for K between 0 and minus 1 is D of X itself. So this is the definition. And let me give an example immediately. So let me give some examples. So the first example is the projective space. So let us take X to be just some projective space, and let us take L to be O1. Then on the projective space we have a standard exceptional collection constructed by Belenson long ago, which consists of n+1 line bundle. And now note that if you take B to be the subcategory generated by O, then this is a Lefschetz decomposition precisely of the same type, with n, which is called the length of this decomposition, equal to n+1. So the standard Belenson exceptional collection on the projective space gives you a Lefschetz decomposition, a rectangular Lefschetz decomposition with respect to O1. Of course, you can ask about other line bundles on a projective space.
Sorry, and why is it called rectangular? What's so rectangular?
Because the general definition of a Lefschetz decomposition, instead of having just one category, requires to have a chain of subcategories. So you can ask that there is a chain B0 containing B1 and so on, Bn minus 1. And so then you put here B0, here you put B1 and Bn minus 1. And for example, if each of these subcategories is generated by an exceptional sequence, you can represent the form of this collection as a Young diagram. So you put the first, in the first column you put the number of boxes corresponding to the number of exceptional objects here. Then the second column contains the information about the number of exceptional objects here, and so on. So it looks like some Young diagram like this. And then the condition that all these subcategories coincide is the condition that this Young diagram is a rectangle. So this is why it is called rectangular. I don't know. I mean, so I don't. I couldn't invent a better name. Of course, this name is not very good, but if you suggest another one, we can try to change. No? You don't want any kind of responsibility. Okay, so so another question is what about other line bundles? And of course, you can sometimes you can modify this exceptional collection also to be to work with other line bundles. So, for example, assume that D divides n plus 1. Assume that we have some integer which divides n plus 1. Then this Berenson exception collection also can be considered as a rectangular Lefschetz decomposition with respect to O of D. Namely, you take V to be generated by first V objects here. Yeah? So if you take this subcategory, then when you tensor it with O of D, what you get will be the next segment in this exceptional collection, and so on. Of course, if you don't have this divisibility, then still you can construct a Lefschetz decomposition in this more general sense, but it will not be rectangular. And of course, you can hope to get a rectangular decomposition only when the rank of the Grothendieck group is divisible by something. So, yeah, so, and of course, this is a very general construction. Of course, it is trivial, but still it is convenient to remember. If you have some Lefschetz decomposition of length m, and if you have some d which divides m, then of course you can replace L by L to the power d, and combine several components into the first component of the bigger decomposition and get from it the decomposition with respect to L to the power d. Okay, so these are, in a sense, trivial Lefschetz collections, Lefschetz decompositions. Let me say some words about more complicated examples. So, first of all, let me mention a general result, which is a nice theorem proved by Anton Fanarev in his paper. So, this theorem says the following: that assume that k, let us take two co-prime integers, k and n, so that k and n be co-prime, and consider Grassmannian kn. Grassmannian k-dimensional subspaces in a vector space of dimension n. Then, derived category of this Grassmannian has a rectangular Lefschetz decomposition with respect to O1. So, in fact, this Lefschetz decomposition is very explicit, and it is related to a very interesting combinatorics. In fact, if you look at the standard exceptional collection of the Grassmannian, which was constructed by Kapranov a long time ago, so it's the objects in this exceptional collection correspond to Young diagrams inscribed in the rectangle of the size k times n minus k. So you can consider some Young diagram, and these Young diagrams corresponds to objects of this exceptional collection. And the nice observation is that there is an interesting action of the cyclic group Z mod n, Z, on the set of these exceptional collections, which is constructed like this. If you have a Young diagram like this, you can think about this Young diagram as about a path going from this vertex of the rectangle to this vertex. Then you can extend this path periodically to get an infinite periodical path. And then you can just move your origin, point of origin to the next integer point on this lattice. So from a Young diagram like this, you will go to a diagram like that. So there is an action of a cyclic group like that. And for example, if k and n are co-prime, then this action is free. This is a particular case. And the objects which form the first block of this Lefschetz collection correspond to orbits of this section. In fact, you can check that in each orbit there is precisely one Young diagram which lives above the diagonal in this rectangle, and these are precisely the objects which form this state. So it is very nice and very explicit. For example, so let me give some examples. So as a first example, let us take the simplest non-trivial Grassmannian with k and m co-prime, which is G25. Yeah, in this case, you are interested in Young diagrams inscribed in this rectangle of size 2 by 3. So there are 10 such diagrams, and you have a three-action of C mod phi. So there are two orbits, and the orbits correspond to Young diagrams which live above this diagonal, and so there are only two such Young diagrams, the empty diagram and the diagram consisting of just one box. Yeah? And so this B is generated by the corresponding vector bundles. The first one is just the structure sheet of the Grassmannian, and the second one is the topological bundle. And so the statement is that you have a rectangular Lefschetz decomposition corresponding to this pair of exceptional bundles. Yeah, U is rank 2 tautological subbundle, and this is V2. If you want, you can replace it by U, then you should interchange them.
Does Z mod n acts geometrically on the Grassmannian, or it acts on the...
No, it acts combinatorially on this combinatorial data.
It doesn't come from...
Yeah, so it is a very good question, how does it generalizes to other homogeneous spaces, and I don't know the answer. So we have some guess about Lagrangian Grassmannian, but I mean, it is not clear. So definitely there should be some interesting combinatorics, and it looks like it should be related to Ginsburg models associated with Grassmannians, but it is not clear. So this is what you have for Grassmannian 2π. And let me give you one more example. Let us take also Grassmannian 310. So I will explain a bit later why it is why do I consider this particular Grassmannian. In this case, you should take rectangle of the size 3 by 7. Just like this. We should again draw the diagonal. And we should consider all Young diagrams which live above this diagonal, which means that they should be subdiagrams of this maximal diagram, which means that this B is generated by Schur functors of the form sigma A B U dual with O greater than A, greater than B, greater than 0, and O greater than B. So these are the conditions. So there is a Lefschetz decomposition like this. So it is always, so maybe I should also write it here, of length. So the length of decomposition is always n in this case. And in fact, if k and n are not co-prime, you still have a Lefschetz decomposition, but it is not rectangular. It is more complicated. So this is what you have. Yeah. And now let me give a general result which says how one can get a CY subcategory from this data. In fact, it turns out that as soon as you have a rectangular Lefschetz decomposition for some variety, it gives you a Calabi Yau subcategory in the derived category of some divisor in this variety. So let me state the result. So let X be smooth projective as usual, and assume that it has a rectangular Lefschetz decomposition with respect to some line bundle. As usual. And assume that Y in X be a divisor in the linear system corresponding to some power of this vector bundle. So smooth divisor. And assume that D is less than or equal than F. Then let me also denote by C the greatest common divisor of D and M. Okay, so D is this D, and M is the length of the decomposition. Then you can check that derived category of Y has a semi-orthogonal decomposition of the following form. So it has two pieces. The first piece comes from the semi-orthogonal decomposition of the ambient category. In fact, what you can check that if you consider the restriction, the derived restriction factor from d of x to d of y, then it is fully faithful on this component B. And moreover, if you take m minus d components like this, they still form a semi-orthogonal collection of subcategories. So let me write it like this. So in some sense, we just forget the first d components from the original decomposition, and there will be an additional component which I will denote by A5. So there is a semi-orthogonal decomposition like this, and this subcategory AY has the following property. If you take its Serre factor, then if you raise it to the power d over c, then this will be isomorphic to the shift by d over c times dimension of x plus 1 minus 2m over c. So note that c is a divisor of both d and m, so all fractions which you see here are integers.
Any d is okay? Any d?
Any d which does not exceed m. So for any d, you have such subcategory. And so, for example, you see that, of course, in general, you don't have a complete information about the Serre factor. You have only information about its power. But if c equals to d, which means that in case when d divides m, then c equals to d. So here you have just the Serre factor itself. So let us see what do we have in some examples.
So this J then it's okay. It's the local begin with the derived.
Yeah, but this is why I mentioned it. Huh?
So we didn't the linear section of the
Yeah. This will be one of the examples, of course. This is why I mentioned Grassmannian 310. I mean, it would be strange to go from Grassmannian 2.5 directly to Grassmannian 310 without any reason. And the reason is precisely because it was in your paper. So, but before going to Grassmannian 310, let us start with something which is more simple. Let us, for a start, take x to be T5. Yeah, and let us take our standard exceptional collection O1 and so on, O5. Yeah, so the standard Bellingson collection. And then take, let us take D equal to 3. Okay? Then this is, so in this case, M is 5, M is 6. Okay? So we have a rectangular Lefschetz decomposition of length 6. And let us take D equal to 3. So D divides M, which means that C is also 3. in this case. So what we get as a result, we see that if y is in this linear system, which means that y is a cubic fourfold, then the subfunctor of ay, so d over c will be 1, so it will be the shift by, again, d over 1, d over c is 1, so dimension of x plus 1, it is 6, minus 2, 6 over 3. Yeah? So which is 6 minus 4, which is 2. So this is the proof of the fact which was in the beginning. So we checked that indeed for the cubic threefold you get 2 Calabi Yau subcategory.
But higher dimensional cubics work as well, like this.
Yeah. Yeah. For example, you can replace P5 with P8, for example. Let us take P8 and again d equal to 3. Then we will check that the subfunctor of a 7-dimensional cubic is isomorphic to the shift by 3. Not of the cubic itself, but of this non-trivial part of its derived category. So there is a kind of, if the dimension of the cubic hypersurface equals 1 modulo 3, then its subfunctor has a very simple way, simple form. It is just the shift by something.
Is this dimension they are geometric or related geometric ones? Is quite
no, in this case they cannot be geometric because if you compute Cauchy homology, the zero Cauchy homology, I think it will be something like 2-dimensional. So, and for any variety, zero Cauchy homology is at least dimension plus 1. So, if it should be isomorphic to derived category of some variety, then this variety would be a 3-dimensional Calabi Yau, and then its zero Cauchy homology should be at least 4-dimensional, but it is 2-dimensional. But on the other hand, it is a good point because so most probably this is this kind of categories is what should be mirrors for rigid Calabi Yau threefolds. So if you have a rigid Calabi Yau threefold, then its mirror dual should have 0 Picard number. Yeah. So its zero Cauchy homology should be precisely 2-dimensional. So most probably some of the mirrors should appear like this kind, subcategories of this kind. So yeah, so I mean, of course, the projective space itself and this Berenson collection is a very simple thing, but even from this very trivial observation, you get non-trivial results. You get this formula for the subfunctor, which is not very simple. So let me give another example. So let us consider Grossmanian 2-5. So let us take X to be Grossmanian 2-5. Then it has a Lefschetz decomposition with this category B, and it is of length 5. So the last one is like this, M equals 5. And let us take D equal to 2, for example. Of course, this is not the best case because D and M, D does not divide M. So in this case, C is 1. And so this allows you to give only some information about square of the subfunctor. In fact, the formula then gives you that the square of the corresponding subfunctor is isomorphic to what? So you should take D over C, which is 2 in this case. Dimension of X plus 1 is 7, and minus 2 times M is 5, so which is 4. So what you can check in this way, that the square of the subfunctor is the shift by 4, which in some sense looks like the subfunctor itself. You can think about it as about some involution composed with the shift by 2. Yeah. So if you take, if you define tau to be as composed with the shift by -2, then from this formula it follows that tau square is isomorphic to identity. So it means that the Serre functor is isomorphic to tau with the shift by 2. So in some sense it doesn't, it is not of K3 type, but one could say that it is of Enriquez type in a categorical sense. So its Serre functor is not the shift by 2, but it's something which is full torsion composed with the shift by 2.
Its quotient homology is not.
But its quotient homology is completely different from Enriquez surface. So it's, in fact, its quotient homology is the same as of a curve of genus 10. So it is some strange creature. So it has a tail of a curve and a head of an Enriquez surface. So again, I don't know what would be a good name for such kind of creature. So maybe yeah, so but in fact we can transform this example a bit in the following way. So here what we did, we just taken this Grassmannian 2-5 and considered its intersection with the quadrant. Yeah, so since we take d equal to 2, it means that we take an intersection with the quadrant. Let us, before taking intersection with the quadrant, let us first take an intersection with a generic hyperplane. So, which means in a sense that let us take d equal to 1. In this case, what we know that d of x has a semiorthogonal decomposition with 4 categories of coming from the ambient Grassmannian and an additional, so this is x prime, and subcategory ax prime. But in fact, in this case, what one can check that as soon as x prime is smooth, this component in fact is 0. This is a property which is very special for Grassmannian 2-5. In fact, it is related to the fact that it's projectively dual variety, which is the dual Grassmannian, has very high codimension. So typically, these components are completely non-trivial, but in this particular case, as soon as this hyperplane section is smooth, this component is trivial. The reason, I mean, you can prove it quite rigorously, and I can't give you a proof now, but the reason is that the dual variety has very high codimension.
For the purposes of the theorem, it does not have to be an exceptional collection, it can be any hyperplane.
Yeah.
And there is some examples where it's not an exceptional collection, but some other.
Of course, you can start with some projective bundle or something. Then Orlov's decomposition will be obvious.
No, I mean that B is some category that is not clear.
To
B
what?
itself is some more complicated.
Yeah, then B will be the right category of the base. Maybe there are some other examples, but this I don't. Okay, so it turns out that in this case there is no term here. So still this x prime, which is a hyperplane section of x of the Grassmannian 2-5, has a rectangular Lefschetz decomposition. But this time m equals to 4. Yeah? And so you can apply again the same theorem with d equal to 2. And in this case, d divides m. And what you will get in this case, it will be precisely the fact that the Serre functor is isomorphic to the shift by 2. So for a fourfold of the same type, you will have a 2 Calabi Yau subcategory. And in fact, this 2 Calabi Yau subcategory is indeed a K3 type subcategory just because the Hodge numbers of this variety is well known, and if you take the part which corresponds to this subcategory, then it will have the same dimensions of quotient homology as K3 surface curve. So these are, in fact, the varieties which you can obtain in this way from Grassmannian 2-5. These are Fano manifolds of degree 10, which were in the title of the talk. So, by the way, how much time do I have? 20 minutes. Very good. So, and in fact, you can do this. In fact, in this particular case, you can kind of iterate this construction. So you can take intersection of Grassmannian 2-5 with several hyperplanes and one model. In fact, when you intersect with an additional hyperplane, then you will still have a rectangular Lefschetz decomposition. You will not get an additional component. I mean, again, because the dual variety has high codimension. And so you will have a similar formula for the non-trivial component of the quadratic section. And it turns out that as soon as the dimension of this y is odd, the formula will be like this. You will check that the square of the surfunctor is the shift by 4. And for all even dimensional intersection, the surfunctor will be isomorphic to 2. So this is what you can do in this case. And let me also...
The categories are distant not related to each other.
For different dimensions? Yeah, it is a good question. It looks like there are some relations between them. But I mean, the moduli, in fact, it looks like the moduli space of this Fano manifolds of degree 10 has a very interesting structure. But I'm afraid that I don't have time now to discuss it. Maybe Olivier will tell something about this moduli space. So maybe let us discuss it later if you're interested. Because otherwise I will not be able to do what I want. Yeah, so it looks that at least some of them are related, but it is not so easy to prove on the first, on one side. And on the other side, I mean, the relation is not very straightforward. It is quite involved. So let me go finally to this example of Grassmannian 310. Yeah, so let us take X to be Grassmannian 310. Then, as we know, if we take this B in D of X, then it will give you a Lefschetz decomposition of length 10. So it will be a rectangular Lefschetz decomposition like this. So M is equal to 10 in this case. And let us take D equal to 1, which means that we will be interested just in a hyperplane section of this variety. Then what we will see, so let us apply this formula. So in this case, D divides M, so C is equal to D. So the formula which you will get for this subcategory will give you the shift by D over C is 1. Dimension of X is 21. So you should take dimension of X plus 1, which is 22. And then you should subtract 2 times M over C. So M is 10. C is 1. So it will be 22 minus 20, which is 2. So again, you see two Calabi Yau subcategory. And again, if you compute the Hodge numbers of this hyperplane section, then you will see that its quotient homology is the same as that of a K3 surface, so it is a K3 type category. And so it is natural to expect some holomorphically symplectic variety related to it, and indeed there is one which was constructed by Claire and Olivier. But in fact, I don't know whether there is a description of this variety as a modular space of some objects on this hyperplane section. Probably there is, but I don't know.
And the holomorphic symplectic variety related to the previous example?
Yeah, this example, in this case, the variety is EPW sextic. So the double EPW sextic. In fact, if you consider the fourfold in this picture, for example, if you consider the modular space of phonics on this fourfold, then it has a structure of E1 vibration over the double EPW sextic. This is very parallel to the Len Serger and Van Straten example, in which case they considered the modular space of twisted cubics on a cubic fourfold, and it had a structure of more or less P2 vibration over some homomorphically symplectic variety. So in some sense, this additional P1 of P2 vibration corresponds to the fact that the modular space you start from, it corresponds to objects which are not in this subcategory. And to get a modular space of objects in this subcategory, you should somehow project, and this projection gives you this non-trivial factors. So, in some sense, there is a P1 or maybe P2 family of objects in your modular space which project to the same object in this subcategory. So if you write down this projection factor, it gives you a non-trivial morphism on the modular space.
It is given schema of surface.
Okay.
Copies of G36 contain
In this Grossmanian
in this hypersurface X.
yeah, so probably probably if you project it to this subcategory, then this will give you a kind of an explanation. Yeah. Okay. So maybe before I go further, let me give some kind of modification of this theorem. In fact, there is a nice modification which shows that instead of considering smooth divisors in your variety X, you can consider twofold coverings, and you get almost the same results. So this was theorem 1, and theorem 2 is the following. So assume that you have the same assumption, so d of x has a rectangular depth decomposition, and assume that y, in this case, not a divisor, but instead a twofold covering of x, ramified in a divisor, in a smooth divisor D, which lives in a linear system corresponding to the L to the power 2D. Smooth divisor. So this is the twofold covering ramified in this divisor. Again, let C be the greatest common divisor of D and M. And then, again, the result is that you have a semiorthogonal decomposition of the same type. And you have a pretty similar formula for the Serre factor of this category, but with some small differences. Again, the formula is for the d over c power of the Serre factor, and again you have the shift, which is very similar. You take d over c dimension of x plus 1 minus m over c. So in this case, there is no this 2 factor, so you have just m over c. And also, but also you have another input from the involution of this double covering. So since you have this double covering, it comes with the canonical involution. In fact, we have this involution to the power m minus d over c, composed with this t. So the formula is a bit more complicated because of this hyperelliptic involution. But first of all, this is an involution, so as soon as m minus d over c is even, you can forget about it, so it cancels out. And also, even if it does not, still we can think about this formula as a formula for the s to the power 2d over c. Yeah? And in this case, this definitely will cancel out. And so in any case, some power of the Serre functor is isomorphic to the shift. So maybe a figure power. So, you can find some examples of Calabi Yau categories from this statement as well. In fact, for example, if you start again with Grassmannian 2π and with this exceptional collection, then you can do almost the same construction. You can first take several hyperplane sections of this variety, and after that take a twofold covering ramified in a quadratic divisor. So it will be also a Fano variety, also on degree 10, and in fact it lives in the same deformation family as the previous one. And it is funny that still you will get the same formula for the Serre functors. So for odd-dimensional varieties of this type, you will have the formula which will say that the square of the Serre functor is the shift by 4, and for even-dimensional, the Serre functor itself is isomorphic to 2. So this kind of hyperelliptic examples also give you more or less the same result. And I mean, so you can play with this formula, and you can find, I think, some other examples of 2, 3 Calabi Yau categories. And I mean, you can do it also in other situations. For example, you can start not with a projective space, but with a weighted projective space. In a weighted projective space, you also have a nice rectangular Levsin decomposition, so you can see what kind of restrictions you get on weights and on the degree of your hypersurface if you want to get some Calabi Yau subcategory. So you can construct indeed many examples like this.
This is the related constructions, right? If you have the double cover, if you have an unsection component for the variety smoothable, just take a component, then take quadratic section. It's smoothable once. You can just take a quadratic section. So these involutions to take the same kind of involvements.
You mean this involution here and that involution there? Yeah.
I mean, first you take its section and then it's double.
Yeah.
The same is taken. Same process.
So I think that I don't understand completely what you are saying, but what is definitely true is that this
side can this right. But on the right there is no power, on the left there is power. Is it hidden?
So,
the degrees are quite different.
So what I want to say is that definitely, so there are two types of degree 10 Fano manifolds. One is obtained as a linear section and then quadratic section. Another example is a linear section and then twofold cover. And as I already said, varieties of the same dimension, but of two different types, in fact, are in the same deformation family. In fact, those which are twofold coverings are degenerations of those which are quadratic sections. And so, in particular, these categories also come in a family. You can consider a category, the non-trivial part of the category of the double covering as a specialization of the category of the quadratic section. And so, of course, in this family, Serre functors also behave nicely. So,
I mean, the star on the right-hand side is the same as the star on the left-hand side.
What I want to say is that this tower specializes to this tower in this particular case, just because it is, in both cases, it is just the composition of the Serre functor and the shift by minus 2. Yeah. For coverings of high degree. Yeah. This is a very good question. Unfortunately, there is no formula for coverings of high degree. And so let me tell you what is so special about twofold covering. In fact, if you consider, so we have two situations. We have either a divisorial embedding situation or the twofold covering situation. Yeah? So let me denote this morphism by F in both cases. What is common about these two cases is that if you consider the push-forward functor, it will be spherical functor in these two cases. which means that if you compose it with the joint function, it will differ from the identity by an auto-equivalence. And this is what is really important for this theorem to be true. You have this property for a divisorial embedding and for a two-fold covering. But for a triple covering, for example, it is not a spherical factor. So this result does not apply, and I don't think that you have something like this for triple covers. Yeah. So in some sense, double coverings are very natural from this point of view. Okay, so do I have more time?
There's some analogical statements for topology.
So I don't know anything about yeah, so let me stop.
Okay.
Questions, comments? For this K3 category study, sometimes geometry